So, welcome everyone. This is going to be our second class about Weierstrass semigroup and code theory. So today I'm going to talk a little bit about the Weierstrass semigroup in 2 points. And well, we are going to do some examples to see how we can manage things when we want to construct the real codes, construct explicit codes over an algebraic curve. Okay, so Weierstrass semigroup at 1 and 2 points. So we have we have a function field. Okay, and a place. Okay, so a function field over the field F, and we fix a P, a rational place. What is a rational place? It means that the coordinates of your points are over the field K. Or, as you said yesterday, this means that the degree of the place is just 1. Okay. Then, fixing this, we saw by the Weierstrass gap theorem that we can associate a Weierstrass semigroup. So we are going to take the Weierstrass semigroup at this point on the function field at this place. So it is just the numbers S, such that the dimension of the Riemann-Roch space associated to the divisor S minus 1p is equal to the dimension of the Riemann-Roch space associated to the divisor SP. So these are what we call the yesterdays. These are the non-gaps at P. So this is the Weierstrass semigroup at P. These are the non-gaps. So, okay. Oh, sorry, I did the non-gaps. So like this, okay? So when you have that these guys have different dimension, it means that you have a function here that's not here. And this you can check. This means that there is a function with a pole divisor exactly equal to S. Okay, so this guy is also equal to the natural numbers S, such that there is a function in S with pole divisor equal to SP. And well, we know that 0 is always here, and we also know that it's a semigroup. It means that if you have S1 and S2 here, then you always have that the sum is in the semigroup. Okay? And what else can we say? So we have this. 0 is there. It's closed under addition. And we also showed yesterday that, well, if S is large enough, everybody is in the semigroup. What do I mean about being large enough? It means that if S is larger or equal than 2G minus 2, then, let me see, 2G, then we have that S is always in the semigroup. Okay? So actually, and who is G? Well, G, as yesterday, is the genus of your function field. So we have all these properties, and we know something else, no? We know that, so for S larger than 2G, everybody is here. And what happens if I do this intersection then? What can I say? Well, so I'm looking to the number of known gaps, and yesterday we saw by the Weierstrass theorem that the number of known gaps is exactly G. So there are G guys in the semigroup and in this interval, okay? And we also have the number of gaps. So what was a gap? A gap is just the natural numbers in the complement. So gaps we have defined as n less the elements in the Weierstrass semigroup. This is the gap set at P. And we know also that the number of gaps is exactly G. Okay? So what we'd like is, can we compute HP? Like if I give you a function field a place of degree 1, can you give me who is this guy? So, well, for any functional field, this is not really easy, but I will do now an example. It's a very classical example. So just to compute the Weierstrass semigroup at the only point at the infinite in the Hermitian function fields. Okay, this is a classical example. And for doing that, I will need to recall, well, I will need to talk a little bit about places in the rational function field and how they behave in extensions. Okay, so what can I say about, let's say we have, well, the rational function field. Okay, so these are just fractions. The denominator and the numerator are polynomials on x, the variable x. So this is the function field of a line. So who are the places in this function field? So places so we can show that the places here, there is a bijection between places here and polynomials. And well, let's say degree of f equal to d. F can, oh, okay, it's something like this. F polynomials, there is a bijection between this union one guy. That we'll call infinite. Okay. So how do you do these places? Well, if you take a polynomial here, okay, you associate the place to the polynomial PF. And well, who's this place? Well, this place is a place such that VP F of F is 1. Okay? What are we saying? We are saying that F is a prime element at this place. And how I compute the evaluation in another element in the rational function field? Well, if you take Z here, a rational function, we know that you can write Z equal to, let's say, Gx over Hx for G and H polynomials. Okay. So if I want to compute the evaluation on Z, we have seen that this is just the valuation on G minus the valuation on H, X. Okay, because this is the inverse of a polynomial. So I have minus here. So I just need to say how we compute the valuation here, P, in a polynomial. I don't need to say in a rational function. Okay, if I know how is this, I know this. So what do you do to compute that? Well, you are in the place defined by the polynomial f. So what you do is you just factorize your polynomial. So this is going to be like, oh, sorry, I forgot to say here, f is here and f is irreducible. This is very important. Yeah. Okay. So irreducible polynomial. So I can factor f is just like fx in a certain power. Let's say g1 of x. And f does not divide g1. So any polynomial I can write like this. Yeah? And if I do so, I just say that the valuation VPF of G, it should be the valuation of this, it's just going to be L, okay? And this L, look, this L is always larger or equal than 0. Okay, so this is L. And so you see, like, for example, if L is 0, means that f does not divide the polynomial G. Okay, so for example, imagine your polynomial here is a degree 1 polynomial. So if f is a degree 1 polynomial, f divides, the condition that f divides G means that if f is a degree 1, f is like x minus alpha. So if f divides G, it means that alpha is a root of G. Okay, so every time that alpha, if it's a degree 1, if alpha is not a root of G, what happens? The valuation is just 0. Okay, so this is what we have. And something else, yesterday we have always been taking K to be a field and algebraically closed. But now we don't want this anymore. Because if you are over an algebraically closed field, then all the irreducible polynomials, they have degree 1. Okay, so you just have places of we are just going to have places of degree 1 here. So for reducible polynomial, this is the place. And and you have this extra here to the infinite, you just associate, we call that the place at infinity. What is this place to the infinity? How can we characterize it? I just give you the how the valuation acts in a polynomial. If I say that, giving the valuation is the same thing as giving the place. Okay? So if you take G, a polynomial of degree n, so we say that the infinite, the valuation infinity computed at G is minus n, is minus the degree. Okay, so in particular, we have, for example, that this is just minus 1. Okay. And this is why we use like the name, so this is P infinity. Why? Because it's a pole of the function x. It's a pole here, because the valuation in x is just minus 1. Do you remember from yesterday, if the valuation on the function is negative, we say that the place is a pole. If the valuation is positive, we say that the place is 0 of the function. Okay, so we have this. And where else? We also have that what is the degree of the polynomial associated to this guy? We can prove that this is just the degree of the polynomial. Okay? And this guy has degree 1. The infinity has degree 1. And well, where else? Okay. So now, what am I going to talk now? I will talk just about Kummer extensions because these are the examples we are going to work here. But well, in the general case, for any function field, algebraic field, algebraic curve, things work. They are a little bit more general. Okay, so suppose we have something like this, a function field. So what do we mean about that? Well, we mean that x and y are functions, and they are like they satisfy a certain relation. They are zeros of a certain polynomial. So we can say here, for example, that f of this f is not that f, but f of x and y is 0 for some f here. So we are taking a polynomial in 2 variables, and we are taking it absolutely irreducible over the algebraic closure, and it's also no singular, and you have to consider the zeros of it, and so this is the function field we have. So if we suppose that the degree of f in terms of y is m, let's say that the degree of f in the variable y is m. So since the f is irreducible, this has degree 1, m. So just to solve, for example, if you have here an algebraically closed field, then you have we know that this field is infinite, so you have an infinite number of places. But for example, if K is a finite field of order K, so how many places we have? Well, we have exactly places of degree 1 at least. How many places we have? We have exactly Q from this. That's the polynomials of the type x plus alpha for alpha and fq, and one more here. Okay? This is the number of places of degree 1 over a finite field. It's a finite number. But if K is algebraically closed, we have an infinite number of places of degree 1. So we are like this. So if I take a place here, so this is the maximal ideal of a certain ring associated to this field. And well, it can be proved that there is another maximal idea here of this function field, that when I do this ideal intersection kx, I get just P. Okay, so this is like number theory. You can prove these things. So you know that it exists at least one, and actually, what we know is that there exists R guys. So Q1, QR, at least one, and at most R, and this R cannot exceed M. Okay, so R is at most M. And well, now we have 3 important guys associated to this place. So we say that this place is over this place. This is our notation. And we have what we call the ramification index associated to the place here and here. So what is the ramification index? So if I take Ki over P, the ramification index this is a number. Actually, it's a natural number such that for any function in S, we have that if I compute the valuation associated to the place Qi, so this is always this number times the valuation of P. Okay, so I need to take the function down here, actually. Sorry. So if I take any function here, and I want to compute the evaluation of this function up here. So this is be given by this equality. Okay, so this is it. So this is the ramification index. And we have something else associated to these plates. That is if I have Qi over P, we have the relative degree. So let's just recall from yesterday. What was the degree of P? It was just the degree of the extension of these two fields. Okay, so this was a ring. This was its only maximal idea. So this is a field. So I have a field extension. It was this degree. So what's going to be the relative degree? Well, associated to this place, Qi, I will also have a certain valuation ring, and I can do the quotient of the place, and this is going to be again a field. So the relative degree f of Qi over P is just the degree of this extension. O over Qi over P. Okay. So this is what we have. And now we have something really, really important for function fields. That's the fundamental equality. So the fundamental equality what it does? Well, you take a place down here, you take all the places over. So for each place you took over, you have the ramification index here. And you also have the relative degree here. And well, this number, they are all related. They are related with the degree of your function field extension. So this is a theorem. So in general, what we have is the sum equal to R of this guy this is just the degree of your extension. So this is in general. But here we'll be working with Galois extensions, Kummer extensions that are Galois. So if you have a Galois extension, what is a Galois extension? Normal and separable. So Galois extension. So for Galois extensions, what we have is something really nice. That actually, the ramification index, it is the same for all the places. So this number is going to be the same for this guy, the second, this. And also, the relative degree is the same for all these guys. Okay? That's it. So if I have a Galois extension, if these guys are all equal, what we have is that this guy times this guy times R. What is R? R is the number of places over your place you have fixed. This has to be the degree of extension. This is M. Okay? So I think that with this, we are able to do our example over the Hermitian functional field. So we are going to take the Hermitian functional field with us throughout the week. And any questions? Okay, so I'll just go on. So let's keep in mind what we want. We want the Weierstrass semigroup at a certain fixed point over the Hermitian functional fields. Okay. So let's take the Hermitian. Functional fields. So we have k of x and y. So this is the equation. So now it's going to be over FQ. So who's FQ? FQ is the finite field with Q elements. So Q is a power of a certain prime you have fixed. Okay. So for the ones who have studied a little bit of field extensions, you see, this is just the norm from FQ square to FQ. This is the norm. And this is the trace function from FQ square to FQ. So this is how we do Hermitian. And well. So let's take, for example, the place. Okay, so now who is this guy? This guy is just and actually, okay, here. And okay. So let's take just the place P infinity. We have this place, this is a rational functional field, and I have this place. So let's take one guy over it. Okay. So I want to know how many guys I have over this guy. What is it ramification index? What is it relative degree? Can we compute this? So let's try to do it. We have the equation and we know how things to do. So what to do? So we have this. Okay. And I have the equation. So if I apply VQ of y to the q plus 1 has to be equal to the VQ to xq plus x. Okay. And okay, I didn't say that, but it happens that, well, this has degree q plus 1, and this is Galois. Okay. So we know that the fundamental equality is going to be this one. Note that by the fundamental equality, we have that the ramification index is always less or equal than the degree of our extension, and also the relative degree is smaller than this, because these are all positive numbers. So we have this. So this means that q plus 1 VQ of y has to be equal to this. And now, well, since this function is down here, for this function, the function is down. So I know how to compute VQ of the function. It's just the ramification index times this. So this has to be times this guy. Can you see here? Or yeah. Okay, I think you can see. So this is just the ramification index. And how much is the evaluation at the infinite in a polynomial? This is just minus the degree. So this is minus q. Okay? So we have this is minus q. Well, so we have that this q plus 1 times the evaluation has to be equal to the ramification index times minus q. Okay, so what happens that q plus 1 is coprime with q. These guys are coprime. And I know that this guy is at most q plus 1. So the only way to everything be okay, what is it? Is that we have the evaluation VQ at y equal to minus q, and this equal to q plus 1. So from this, what we get is that and this guy well, and now we have the fundamental equality. Okay, because well, I already know something. I know the ramification index, but what is the relative degree and how many places I have over? So this is Galois, and I have this, and I have this. So from the fundamental equality, we know that this guy, remember they are okay, they are all equal. So for all the places over P infinity, so I should have this, and R. So I have like a Q, QR. So one, so suppose we have this. But these all have to be Q plus 1. And we already computed the ramification index. This is Q plus 1. So we need that actually, then we conclude that we have R has to be 1. Only one place over it with relative degree 1. So we don't have these guys. Okay? So this is it, and we know that this guy, the ramification index here is just Q plus 1. Okay? So I have this. So, well, note that if Q is over P infinity, okay, so we have this. And so we have just one guy over, and you are going to call him like Q infinity. So what we want to compute now is this guy, who is the Weierstrass semigroup at this guy. Well, I know something already. I know that these are the non-gaps. I know that the number of gaps is the genus of the curve. That for the emission is just a Q minus 1 over 2. So, okay. Now, why the genus is this? Well, because it's not hard to show that, well, this is actually is a reducible curve, non-singular. Oh, non-singular we proved yesterday, and it's reducible of degree Q plus 1. So what is the genus? The genus is Q plus 1 minus 1, Q, times Q plus 1 minus 2, Q minus 1 over 2. Oh, that's the genus. Okay. So we have the genus here. And this is the guy. we want to know. So for doing that, do you remember finding Weierstrass semigroup? You need to find functions with a certain pole just at this point, and well, with a certain order. Okay. And look, this is the equation. So of course, if a place is a pole of x, it's going to be a pole of y also, because it's a polynomial. So what we are going to do now, we are going to compute the divisor. We are going to compute the divisors of x and y in the Hermitian function field. So this is H. Okay, H. How do you say it's a beautiful H, different from the regular H here. So, yeah. So how we compute the divisors? So I will compute the divisor of x, and then as an exercise, you can compute the divisor of y. Okay. So let's suppose that. I want to compute the divisor of x. So who are the zeros of x here? Well, x down here has only one zero. It's 0. 0 is a zero of the function x. Okay, so. And I will denote like this. So P0 is the place associated to x. Okay, usually we do like this. P0 to x equal to 0 is the only zero of x here. Down here. So if I want to know how many zeros it has up here, what should I do? Well, I suppose I'll take Q, a zero of x up here. So now we are like this. We have here. And we take a place up here. And again, we want to know well, how many zeros this function has up here? What is the order? Okay. I'll have this. So let Q over P0. Go like this. Oh, what do you mean when you say that it's a zero of x? Well, you are saying that this is larger than 0. Yeah? Okay, larger. So again, we just play like we did here. So I get that Q plus 1 has to be equal to the and wrong. But now I have this. So now it's different here. Huh? So I just did the same thing we did there. Okay. So I have this, and what we can conclude. Well, look. How I compute the valuation at the place associated to the irreducible polynomial x. I have to factorize this polynomial by x. But this polynomial is just x times xq minus 1 plus 1. And you see, and of course, x does not divide this guy. Because 0 is not a root here. Okay, so we have this. So it means this function is x to the 1. So this is just 1. So I get this is equal to this. Okay. And by the fundamental equality, we know that this guy is at most the degree of the extension. That's Q plus 1. So we get this times this has to be equal to that one. That's less or equal than Q plus 1. And here, of course, we have this. So these are all equalities. So we need that this guy has to be 1, and this guy has to be Q plus 1. So and well, this guy is this, and this guy is 1. Okay. And again, no, if I have well, by the fundamental equality, if this guy is Q plus 1, this and this has to be 1. So for this place, I have just one place here. I just call it Q index 0. Okay. So just one place that is, we say it's totally ramified because the ramification index is equal to the degree of the extension. We have this, and this is 1. Okay. So we know that it has only 1 0. And well, now we need to look at the poles. So how many poles the function x has here? Well, it has just one pole, the infinite. Yeah. So if you take Q over the pole, we know that there is only 1. We have done already computations. So we know also that Q infinite is the only pole of x in the Hermitian function field. Okay. And okay, we have this. So what is the divisor of the function x here? So we have that, well, it has just 1 0. And well, this guy is going to give you actually the order of the 0. Yeah. So this is just Q plus 1. Because look, if I compute well, why this is Q plus 1? Well, you just compute. What is this on x? We have proved that is the ramification index times this. And we have proved that this is Q plus 1, and who's P index 0? Well, is the place associated to the polynomial x. So V index Px computed in x, this is 1. So this is just Q plus 1. Okay, so what is the divisor of this function? Do you remember? This is just the sum Vp of x. Okay, let's do like this. Q or Q in the Hermitian function field. But we know already that the function x up there has just 1 0 and 1 pole of order Q plus 1. So this is just Q plus 1, 0, and 1 pole, P infinite. That's it. Okay. Look, what we have done here, we did for 1 0 of the polynomial xq plus x. So actually, if you think the curve over fq is squared, then this polynomial has exactly q zeros in fq squared. And then for each one of the zeros over FQ squared, you have a place here, and you can show that they behave exactly equally as this zero of the polynomial. They are all totally ramified. Okay, it's well, this is an exercise. If I go a little bit higher, I go to FQ squared. Okay, so all the roots, all the elements here, like P index x equal to alpha, where alpha to the q plus alpha is equal to 0, you see, if alpha is a root of this, it cannot be FQ. It has to be FQ squared. So these guys, they all behave in the same way. You're going to hear something like only one place up here, totally ramified. You just do the same computations. So let's come back a little bit to what we want. We want this. What is the semigroup at the point, well, not P infinity, actually at Q infinity. We are looking to the place up there. What is the semigroup here? So we have computed the divisor of X in their Mitchell function field. And you see, we see that this function has only pole at, again, sorry. This function has pole just at Q infinity of order Q plus 1. Well, this means that the Q plus 1 lives in the semigroup defined in the semigroup at the point Q infinity. So from this, we have that Q plus 1 is here. So we get one number there. Now, I'll just let you as an exercise, but well, doing the computations like this, so I'll just say like in a similar way. Oh. We can show that the divisor of y, how do you do to compute the divisor of y? You do exactly like we did here. Well, take a place in the Mitchell function field, suppose it's a 0 of y. And then use the equation of the curve to try to see what happens. So what's going to happen now is that the divisor of this guy is just... so look, if I do a 0 of y equal to 0, I get x to the q plus x equal to 0. So actually, this guy and all this guy, they are going to be zeros of y. So what I have here is that q0 plus, or I can just write like this, the sum from 1 equal to q of q index alpha. Okay, I know there is only one up there, such that alpha to the q plus alpha is equal to 0. So I have q guys. And the poles, well, if you take q a pole of y, you can show that it has to be a pole of x also. So if it has to be a pole of x, since x has just one pole, y has just one pole. And what is the order of the pole? Well, has to be, without calculations now, has to be q. Why it has to be q? Because we know that the degree of a divisor given by a principal divisor is always 0. So this divisor has degree q. And if you can put just one place here at the infinity, it has to have order q. It's the only way that this computation is going to give you degree 0. So we have this. Well, so what we get from this, look, the function y has pole just at q infinity of order q. This means that q also lives here. So q is here. But this guy is a semigroup. So if Q is there and the Q plus 1 is there, the semigroup generated by Q and Q plus 1 has to be there. So and so who is this guy? This is the semigroup generated by Q and Q plus 1. How are the elements over there? Well, are just linear combinations. Alpha Q plus beta Q plus 1. But you can just take alpha and beta being positive. Alpha and beta natural. I mean, they can be 0 too, huh? Okay, so natural numbers, 0 is natural for us. So you have this. And well, now there is something we know, that if you have a semigroup, let's say if this is a semigroup generated by A and B, and the GCD between A and B is 1, then H1 has exactly A minus 1, B minus 1 over 2 gaps. Okay? So, because well, what are the gaps? The gaps in a semigroup are just the missing guys. Okay, so these are the gaps. So look, so this is actually the genus. This is what you call the genus, the number of gaps. Now Q and Q plus 1 are coprime. So this semigroup here, this one has genus Q minus 1, Q plus 1 minus 1 over 2. So the genus of this semigroup, the number of jumps here is exactly the same of the jumps here, the legs, the missing guys. And they are contained, so they have to be equal. Okay, so the semigroup at infinity is generated by this and this guy. Well, in general, for any algebraic curve over a finite field, it's not easy to compute even this Weierstrass semigroup in 1 point, because this depends strongly on finding certain functions with certain properties, if you want to do it in this way. So this is special. This is easy. And we have this. This is well known. Now, so we already know the Weierstrass semigrouping at Q infinite for the Hermitian function field. And now I will move on to what is the Weierstrass semigrouping 2 points. And we want to compute that also. So, Oh, well. The idea of 1 point semigroup can be generalized for two. I will concentrate in 2 points here, but well, there is a lot of work that has been done for more than 2 points. Points. Okay. So we have this, and well, how we generalize? So this is, we just take the same idea. Huh? We have now suppose we have two, Q and Q. In a function field, rational places. We need rational places. Why we need rational places? Because we always want the jumps like this. We want the jumps here from one to the other, the jump of the dimension to be at most 1. So this guy has to be degree 1 place. Of course, you can think about something like, well, you can try to study first a semigroup with this guy like is a place of degree 2 or 3, but then if it's degree 2, the jump here can be more than 1. Okay. So you lose a little bit the control. And also if you have a degree, like if P is a degree 2 over FQ, you just go to FQ square and you get 2 places of degree 1 associated to Q. So P over here will be like this, Q1 plus Q2. So you can always take a degree 1 place. So remember we had this. So this guy, such that there is a function and the pole divisor of Z is just SP. Okay. So how we do for 2 points? Well, you don't want numbers, you want tuples or pairs. So you want pairs. I will fix my notation here. So the pairs will be like alpha, beta. So these are pairs in square, such that the same thing. There is a function in F such that the pole divisor of zeta is just now alpha p plus SQ. So alpha beta. Okay, so you see, it's very natural, the generalization. And of course, I can do this for many points I want. The definition can be the same. Also, well, if here you want to consider not just natural numbers, but integer numbers, there is also a generalization of the classical Weierstrass semigroups to a semigroup that allows you to consider tuples in zeta square. This is a work from Peter Billing and the other guys. Okay? So if you have interest about this, so we have this. And so notice that by definition, we always have that this guy if I just do beta equal to 0, I have this guy is going to be contained here. Of course, if you do this also, no, we have this. So this is just by definition that this set and this set are always contained in the semigroup. So what I plan to do today is, well, to show how can we get this guy. and do an example over the Hermitian function fields. Okay, let's see. So at first, we need to characterize what does it mean a pair to be here. So kind of a lemma. We have data alpha, beta. So we can again translate this notion about the dimension of the certain Riemann space. So this is going to happen if and only if well, let's show this. Okay. Look, when I look to the dimension of the Riemann space associated to this divisor and to this divisor, well, the degree from here to here, the degree grows by 1. So if the dimension is different, it could be just +1. So what you are saying is that, well, this Riemann space is going to be associated to this divisor, is contained here, but it's not equal. It's a little bit smaller. The dimension is smaller by 1. Okay, so to be in the Weierstrass semigroup at 2 points means that these two equalities happen. So let's show this. So yeah, if I have alpha and beta here, well, by definition, there is a function such that the pole divisor is this. Okay, yeah, this is enough, huh? So if this happens, yeah, of course it's here. So the function is, well, this means that the divisor is larger or equal than this. So you have your function in the right place. Okay. And well, and your function cannot be here. Why it cannot be here? Because to live here, in this second Riemann space, we need that the pole divisor, the order of the pole at the function z at the point q, it should be -1, but I know it's beta. So, okay, so it's not beta -1, it's beta. So this puts you the function here. Okay. If it lived here, what does it mean? This means that if it was here, we should have this. The divisor of zeta larger than this, plus minus beta -1 q. Yeah, but what we have is this. Okay. And we don't have that minus beta is larger than minus beta -1. So. So, and well, the same thing for the other one. Huh? Here doesn't matter if I just do. It will be the same. It's not here. So this is okay. And now to the other. How can you prove the other implication? So we have the dimension here is this one +1. So there is a function that is here, is not here. There is another function that is here, and it's not there. Okay, so exists z1 that is this guy, and it's not in this guy. So what this means? This means that at the point P, I have that the evaluation at P is exactly minus alpha, because it's here, it's not there. And what can I say at the point Q? At the point Q, I cannot say too much, but I can say that VQ of zeta 1 has to be larger or equal than minus beta. Yes, so we have this, and we also have a function here that's not there. So in a similar way, we have a second function. So what does it mean? Well, it means that the order of the pole of zeta 2 at the point Q has to be exactly beta. So now we have that VQ of Z2 is minus beta. And for the place P, we just know that the evaluation of P at Z2 has to be at least minus alpha. Okay, so we have these two things. And what we want to show, we need a function that has order of pole at alpha equal to, at P equal to alpha, and at Q equal to beta. So what you do, we just take the sum of the functions, but well, before taking the sum, we have to look at something. If this is equal, well, if this is equal, then we are done. Then the pole divisor of this is just alpha P plus beta Q. So if I have equality here, we are done. And also if you have equality here, we are done. If this is an equality, we put zeta 2 that was living here and not here, he will be here, okay? Yeah. No, okay. Yeah. Okay, just a minute. I just did something that is not really right. So if it is equal beta here, it means that zeta 1 that lived here is also going to live in the second one. And so the pole divisor of zeta 1 is going to be this guy. In the same way, if you have equality here, this will put you zeta 2 here also. So it was here, it will be here also, and then we get that the pole divisor of so if this happens, then we get that the pole divisor of this guy is this. Yeah, and any of these cases tells you that this is in the Weierstrass semigroup at the 2 points. So we can just consider that we have inequality here and inequality here. This is the case. Now suppose that VQ at Z1 is larger than minus beta, and VP at Z2 is larger than minus alpha. So what we need? We need a function with a pole only at P and Q of this order. So we take the function that is the sum, zeta 1 plus zeta 2. This guy. So what is? So at first we notice that if R is a place and R is not P and Q, so what is going to be the evaluation of R at zeta? Well, this is evaluation. So this is larger than the minimum of the evaluation of R at zeta 1 and zeta 2. Okay. But zeta 1 lives here. So zeta 1 can only have poles at P and Q. Out of these places, it could have at least zero, it could have zeros or could be equal to 0. So this number is always larger or equal to 0. This also, so this is larger or equal to 0. So if R is not any of these places, we know that the evaluation is larger or equal to 0. So this function can only have poles at P and Q. So let's compute VP at Z. Again, this is evaluation. So VP at Z1 plus Z is the sum. And what we know? We know that V in XP at Z1 was minus alpha. So this is minus alpha. And we know that VP at zeta 2, this is larger than minus alpha. And we saw yesterday, well, if the evaluations are different, this is an equality, and this is equal to the minimum. And then we are done. So this is not actually this is equal, and this is equal to what? To the minimum. And who's the minimum? Minus alpha. And now, yeah, so now it's going to happen the same thing if you consider the place Q. Okay, you get that VQ at zeta is also equal to minus beta. And then zeta is the function we are looking for. So you just fill up here. And this implies that, well, this guy. So this is the condition. Okay, to being the Weierstrass semigroup at 2 points. And no. So now we need some time to prove something very, very interesting. That we are going to show. We can, well, we can obtain, there is a way to get this one. From the gaps at the point P and the gaps at the point Q. Okay, so from the knowledge of these two, we can recover this one. So we need two lemmas to prove this. So we start by lemma 1. So before lemma 1, I wanna define something. Because it's like this. So if you have two vectors, well, living doesn't matter where, but okay, you can just put here. Then we define so this is going to be vector x1. This is vector x2. Then we define the LUB. of these two vectors. This is the least upper bound. So what's going to be the loop? Is just in each coordinate, you take the maximum. So this is a vector where the first coordinate is the maximum between alpha 1, beta 1. And the second is also the maximum between alpha 2, beta 2. Okay. So what we are going to prove first is lemma 1. Is that if you take alpha, beta, and this guy, two pairs in the Weierstrass semigroup at 2 points, with the conditions that suppose that alpha is larger than beta. So we don't want this larger than this and this larger than this. We want this larger than this and beta prime larger than this. Is alpha larger than alpha prime? So this guy is larger than this, and this is larger than this. What we're going to show is that the loop then, what is the loop of these two guys? The maximum between alpha and alpha prime will be alpha. The maximum between beta and beta prime is beta prime. So the loop is here. Okay. This is interesting because this gives you a way to find new non-gaps here. Well, so again, if you have equality here or equality here, then you have nothing to do. Because if alpha is equal to alpha prime, then the loop should be alpha prime, beta prime, and this guy was already there. So you don't need to prove. So if alpha equal to alpha prime or beta equal to beta prime, it's not. Okay? So the interesting case is when this is larger and this is larger. So suppose so again, we have that these both pairs are in the Weierstrass semigroup, so there is a function such that this is just alpha p plus beta q. There is another function such that whole divisor is just alpha beta, alpha prime p plus beta prime q. And you consider again the sum. So this guy is gonna work to show that this is happening. Yeah, because why? Because if I do, who is the just as we did before, for any place different from P and Q, this place cannot be a pole of the function zeta. This is the comment we did there. And again, if I do now, what is the evaluation at Z? This has to be larger or equal than the minimum of this one, and VP, we have 2. And we know that how much is this? It's just alpha. And the VP at zeta 2 is just alpha prime. Okay, actually it's not alpha because it's a pole, so it's minus and minus. And well, since we are in the case that they are different, again, this is an equality, and you just take the minimum. So the minimum between this is minus alpha. So this is just equal, and this is equal. And in the same way for the, okay, if you do like for Q. So we have that this guy has pole divisor exactly what we wanted. That was alpha P plus beta prime Q. So yeah, so if you take two pairs in the wher semigroup at 2 points, the loop stays in the wher semigroup. This is what we have proved. So I need a second lemma that is just, well, it's technical one. So let me. I'll just write lemma 2 here because I want to keep them in the blackboard because we're going to use them a little bit in a few minutes. So this was lemma 1. So lemma 2 says to you this. That, well, if you have, again, alpha beta and alpha prime beta, now here, so one coordinate is the same, a pair, and this coordinate is at least 1. So beta larger than 1, and well, 1 is larger than the other one, so I can just suppose that alpha is larger than alpha prime. Yeah, they keep, if they are equal, we don't have anything. So if this happens, then what happens that exists a delta, and this delta is smaller than beta, such that alpha delta is also here. So we have a pair, one coordinate equal, beta is not 0, it's at least 1. This is larger than this, so I can find someone smaller than beta such that this guy is still in the same group. So let's prove this. So proof. So again, I have these two pairs here. So we have a function for each pair such that the pole divisor of the first function is alpha p plus beta q. And the pole divisor of zeta 2 is zeta 2 alpha prime p plus beta q. So look, now if you add the functions, you get nothing because the evaluation at q of zeta 1 is beta and this is beta equal. So if the evaluations are the same, I cannot do anything. So we'll do something different now. So we are going to look locally, we are in a function field, we are going to look locally at the point q. So let T be a prime element at Q. Okay, so we said yesterday, if I have a prime element at T, element t at the point q, any function in the function field, I can write as a power series in t. Well, I can write zeta 1. So what is the order of the pole of t at q? Is beta. So it has to be t to the minus beta times something inversible here. So here it should be something like a0 plus a1t plus t squared. Okay, well, finite sum, and this cannot be 0. Also, for zeta 2, locally at the point q, I know that this function can be written like this. So where a0, a1, these guys are just from the base field. Huh? 0, so this is not 0 also plus beta 1, beta 2 t squared with this guy. Okay. So what we want? We want a function with pole art at the place q is smaller than beta. So the nice function is, if I take zeta equal to beta 0 times zeta 1, and I do minus a0 zeta 2. Okay, so if I do this, what's gonna happen? I'm gonna cancel this first term. So this is going to give me something like a1 t na minus beta plus 1 and okay, plus a2 t na minus beta plus 2 for the first guy. And for the second guy, I have just beta 1 t na minus beta plus 1 plus beta 2. So you should define zeta like this. You see, you cancel this t to the minus beta. So now what happens? Well, it could happen that this is, this could be 0 too. I don't know, you know? A1, oh, sorry. Here it's missing something. It should be beta 0, this. And here it's missing the A0. Okay. Well, it could be that beta 0 times this plus beta 0 times A1 minus A0 B1 should be 0 also. But doesn't matter, huh? The order of pole, it could be at most beta minus 1. It's here. So this is the function we want. Okay. So we have that this function certainly at the point q is delta, with delta smaller than beta, because it's here. Huh? But it's this or this or this or this. Huh? We don't know. Like this. And this is just, and we keep everything as alpha. Here yeah. Oh, I don't know exactly what happened at the point P, but it should be, it could be alpha or alpha linear, alpha or alpha prime. Anyway, but I know if I have the two guys, I have the loop there. So I can, using lemma 1, I can suppose that I got this one that is the larger one here. So this is the guy we are looking for. Okay, so who is delta? Delta is at most this guy here. Yeah. So delta is so we have these two. So now we are ready to prove our proposition. So this is a very nice proposition. This is from the work of Halma and Key. They had a sequence of papers. This is like a 2-point codes of their mission. So the proposition is now we are going to relate the gaps at P. Suppose this is just alpha 1, alpha 2. We know we have G gaps. G is the G's. So this is this, and suppose that the gaps at the point Q are just beta 1, beta 2, beta G. Yeah? So for each alpha I here, define beta index alpha I to be the minimum of the gammas such that the pair alpha, the minimum, the pair alpha I gamma is in the wher semigroup at the 2 points. Okay. So you take a gap at the point P and you look to the smaller natural number is gamma larger than 1 such that well, actually I can just put yeah, okay. I'll add like this. Because look, gamma cannot be 0. Because if gamma was 0, alpha I should be in the same wher semigroup at P. But alpha I started here. So yeah, I know it's not 0, but I just write like this. So the minimum of the natural numbers such that the pair is here. Okay. So it's very interesting is that then, so how many betas you have? You have G betas. Then it happens that the set of all these betas is just the set of gaps at the point Q. Okay, then the set of these guys of G, this is just equal. So this is nice. So we are going to prove this using lemma 1 and 2. But so what we have proved after this proposition? Well, we have proved something like this, that it exists a permutation. You got, let's say, sigma from okay, so it takes alpha I to this such that, yeah, if you look to the graph of this permutation, yeah, the graph. So the graph we are going to call gamma. This is just the graph of the function. So this is the set of the guys, alpha I, beta alpha I. So yeah, we know that this set is all contained here. So yeah, how many guys you have in this? This is the graph. Well, this has G. Oh, this has cardinality G. Oh, knowing the gaps at the 2 points, I already have the elements in the wher semigroup. Okay. And we also have proved by lemma 1 that, yeah, if you take 2 any guys here, the loop should be also there. It's lemma 1. So you didn't put just G guys here. All the loops of the elements here have to be here also. So we have put a bunch of guys inside there. Okay, and this is going to characterize the Weierstrass semigroup at the 2 points. This and and some elements we just said a little bit before. Oh. So I will keep the lemmas here and I'll prove the proposition here. So beta alpha is, as we said, it's just a minimum. So, we know that alpha is not here because it's a gap. So as I said before, we know that beta alpha cannot be 0. It's at least 1. Okay. So this is at least 1. Well, so we have one guy, alpha, beta alpha here. With beta larger than 1. Okay. Yeah, alpha is not 0 also, because alpha is a gap. And 0 is always 0 is always here. Yeah. So now suppose what happens if it exists. So this guy is there. Suppose there is a guy is smaller than alpha, such that alpha prime beta alpha is also here. Okay, so then well, what do you have? You have alpha beta alpha here, alpha prime beta alpha here. So yeah, we have 2 pairs. The second is equal. It's larger than 1. So I know there is someone smaller than alpha. Then by lemma 2, it exists as delta less than exists delta is smaller than beta alpha, such that so if there was one smaller, there is a guy smaller than this by lemma 2, such that alpha beta alpha should be here. Yeah, but this is a contradiction with the definition of beta alpha, because beta alpha is the smallest such that the pair is there. Okay, so this is a contradiction. With the definition of beta alpha. Oh, sorry, here was this one of beta alpha. Yeah, because beta alpha was the smaller, so this guy was here. So I found someone smaller. That cannot happen. So what you are saying? So this is very interesting. You are saying that there is no guy such smaller that this pair is there. So this means that you can interchange the things. I mean, it means that alpha is also the minimum of the pair such that alpha beta is there. So it means that we conclude that alpha is also the minimum of the gammas such that gamma beta alpha is here. Yeah, because there is no one smaller than it with this condition. So it's the minimum. And remember, yeah, okay, what we want to show? We want to show that beta alpha actually is a gap at the point Q. This is what we want. So we have that alpha is here. Now, yeah, so our claim is that, well, that beta alpha cannot be here. Why? Well, let's do it. So we don't need this anymore. So I use the lemma 2, and the lemma 1 is just to show about the loop. Right? Well, if beta alpha is here, then 0 beta alpha is here. Yeah, but and then this has to be here, and which contradicts is a contradiction with the fact that alpha was the minimum. Okay, and look, alpha is alpha was in the gap set. Contradicts that alpha is is the minimum, blah 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 blah. That one. Okay. So we conclude that beta alpha actually has to be a gap at the point Q. Okay. So, well, this is true. And now, since the beta is the minimum, okay, so it's clear now from the proof that if you take alpha 1 different from alpha 2, then the betas associated has to be different because they are the minimum. So we have that the number of beta alphas such that alpha is here. So since we have this, we know that this set has G elements. Okay, because the function is injective. And of course, we have proved that this set was contained in this set, and this set has also cardinality G, so they have to be equal. This has G elements, it was contained here. This has G elements. So they're equal. Okay, and this is done. So we know that this set is always there. Now, yeah, so this is done. So how can we get this set gamma? Well, there is a way to do it. Huh? So this, okay, later on, this gamma set will be called the generating set. So let's take again. So we have sigma from this to here that associates to this guy of beta alpha I. This is a bijection. Okay, and we have that gamma is the graph of this. So we have proved that this is always contained here. So we have a lemma that says to you that, well, if you take gamma prime, a subset of GP, Cartesian, GQ, intersection, this guy, and well, and if exists a permutation such that a permutation, power permutation of the set 1G, such that gamma prime is just the guys like this, Li, L prime of tau I. So you are doing what we did with the sigma over there, okay? Because who is this guy? Yeah, this is just a beta of the sigma of I. You can think like that. So we have this. Then gamma prime is equal to gamma. So, okay, so the proof is easy because, well, if you take any permutation of this and the elements like this, well, the permutation I have here was taking this guy the minimum. So this permutation here has to be larger or equal than another one. They are both permutations, so they have to be the same. So you can think about it. You can conclude you have this. So we have this, and look, this is telling you that in a certain way, if you are smart enough to find a subset of elements in the varchar semigroup in 2 points, and here of size G, it has to be gamma. Okay, why? Because yeah, any subset here of size G actually is given by a certain permutation. You can think it's a finite set. So you say, well, this is a finite set given by a permutation. This is true. And so they will be equal. So this is how you do to try to compute this gamma set. So what we have proved, what we have, the following. That characterization. This is important, that the varchar semigroup at 2 points, you just take the root of all vectors x and y, these are vectors, okay, such that, so I'm thinking x and y here, the root of this vector such that the vector is in x and y are in this graph set. So the loop of the guys living here. But we also have these guys, huh? Because remember, the elements living here, they never have coordinates equal to 0. So we are missing some guys, these guys, like, we are missing this. 0, union, 0, HQ. Okay? So, well, so what we have obtained is that if I want to know the varchar semigroup in 2 points, what I need to know is the varchar semigroup in each of the points, and these mysterious sets. But this mysterious set, well, we have an idea how to compute it. It's given here. You just need a subset here of size G. That's going to work. Okay? So this is why we call this like this is a generating set for the Weierstrass semigroup. Generating set of HPQ of this guy. So, well, next class, what we'll do, we will start to computing the generating set over the Hermitian function field for 2 points. I will show you how can we get that. So we start with an example, and then we are going to move on to pure gaps. Pure gaps, they are interesting. They are it's a special subset of the set of gaps in 2 points, and that actually I forgot to define. So we have the semigroup in 2 points. What are the gaps at 2 points? So in the same way, the gaps is just this plus the Weierstrass semigroup. So these are the gaps at P and Q. Well, then do you remember for 1 point, the gap set had size G, order G. Now for 2 points, actually, the order of the gap set, we don't know anymore. It depends on the point you have fixed on your curve, on the places you have fixed on your function field. Okay, it's not the same for in 2 points. And actually, in the work of Holm and King, they showed over the Hermitian that this was not the same for all the points. Well, not sure about that, but I think so. Okay. So I have this. So, well, tomorrow we'll start in computing this for 2 points, and then talk about pure gaps and how can we compute pure gaps over a Kummer extension. So Kummer extension is a special type of a Galois extension. And we know many things about Kummer extension. So it's in a certain way, we can deal with them. Okay, if I give you any algebraic curve, you have to work that own algebraic curve. But Kummer extensions, you can work all the algebraic curves of certain type at the same way. At the same way, no, at the same time, I want to say. So, well, if anyone have a question, you can ask me, you can write there. And well, this is the class for today, and I hope to see you all tomorrow. Okay, thank you for coming, attending.